All right, welcome back, everyone. This is the final AP Physics C 2022 AP exam pre-response questions that have been released. So our last one is for set 2 of the E&M exam. Now, similar to mechanics, set 2 is very similar in terms of types of questions asked, although I do actually think that set 2 is a little bit easier. So it'll be kind of like a nice way to end off this series. So after this, I do plan to cover the AP Physics 1 solutions, though probably not for a little bit of time. And just to kind of give myself a break with recording as well, too. So in terms of this then, let's just go ahead and dive right into it. So for set number 2 E&M, instead of having spheres, in this case, we have non-conducting cylinder in the center and then a thin concentric conducting spherical shell in the outside. So we're given some different things. The important things to note is that the inner cylinder has a net charge of plus Q and the outer shell has a net charge of plus 4Q. And so if I go ahead and I move on to the first page with questions on it, then what we're going to see is that the first question is to determine the charge on the outer surface of the cylindrical shell within the length L. And the answer to this is actually just going to be plus 5Q. Why is it plus 5Q? It's because that inner cylinder has a charge of plus Q, so the inner part of the shell should have negative Q. To balance that out, in order to get a total of plus 4Q, we have to have plus 5Q on the outer shell then of charge. Now for part B, for Gauss's law, we do need to use a Gaussian cylinder. As you can probably tell, our system is made up of cylinders. That means that we, of course, need a Gaussian cylinder to help out then. And so I'm going to say that that Gaussian cylinder has radius lowercase r and length big L then. Now we can actually ignore edge effects typically. And so that's what I'm going to actually go ahead and do here then as well too. If we could not ignore edge effects, then we actually would not be able to solve Gauss's law cleanly. And so it's implied that we can go ahead and ignore them in here. And so in regards to this then, what I need to do is I need to draw out my Gauss's law equation, E dot dA integral is equal to Q enclosed over epsilon naught. Well, because this is a uniform cylinder for the inner cylinder, Q enclosed is going to be the charge times the enclosed volume, or the volume of my Gaussian surface. And so therefore, that's going to be total charge, which is plus Q over total volume, which is pi r squared L, big R. And then the enclosed volume is pi little r squared L. That's the volume of my Gaussian cylinder. Now, because we can ignore edge effects, electric field will be constant across the entire lateral part, not along the faces of the cylinder, but just the lateral parts. So the area will be 2 pi lowercase r times L. Simplifying the right side, I get Q little r squared over big R squared epsilon naught. Therefore, the electric field is going to be QR over 2 pi epsilon naught big R squared L. And that does actually have the correct dimensions. I do need to say outward from the center axis of the cylinder. This does have the correct dimensions. It does look very similar to what you would expect if we had a thin insulating rod rather, back from unit 1 with electrostatics. All right, for part C, it's asking again if little r is bigger than big R, right? If little r is too big R, how does the electric field go? Well, in that case, Gauss's law would tell us a very similar equation. So this would be equal to Q over epsilon naught. The area of my Gaussian cylinder, if little r is bigger than big R, would be 2 pi little r L. Enclosed charge again is just plus Q. So therefore, the electric field is Q over 2 pi epsilon naught r L then. Therefore, E is proportional to 1 over R. So I get 6 newtons per coulomb. Double the radius, cut the electric field in half. All right, part D, derive an expression for the absolute value of the potential difference between the surface of the non-conducting cylinder and the inner surface of the cylindrical shell. So what do we have to do here? Well, what we have to do is we have to take that equation for potential difference. delta V is equal to negative A to B in electric field dot dr. Well, we have our expression for electric field due to part C. So we're going from R to 3R, which is where the conducting shell is at. Electric field is going to be what we found in part C, Q over 2 pi epsilon naught RL dr. Well, 1 over R dr integral is going to give us natural log. So we have negative Q over 2 pi epsilon naught L natural log of R from 3R to R then. All right, and so in terms of this, I can do some manipulation here. I'm just going to go ahead and simplify this down. We've done all of the physics now. It's just a simplification problem. So what I end up getting is negative Q over 2 pi epsilon naught L natural log of 3. And because we are asked about absolute value here, it's important to note that that ln of 3 is actually going to be a positive number. Q is positive and everything else is positive. So the absolute value then is just going to be Q over 2 pi epsilon naught L natural log of 3. You might be tempted to flip the natural log, right? Get rid of the negative sign, then you can say ln of 1/3, but keep in mind that ln of 1/3 is actually a negative number. So this would not be an absolute value then. However, ln of 3 is positive, and so therefore this would give me the correct answer. Ln of 3 is actually negative ln of 1/3. And so again, this does work out to be the exact same thing then. All right, part E, we have to sketch the electric field as a function of R. Well, we know in section 1 that we have a linear increase. We know in section 2, we have a 1 over R decrease. And then when I get to the conducting shell, what I should expect to see is, because the enclosed charge now goes up all the way over to 4Q, or just higher than what it would have been when I reached the edge of section 1, I should expect to see something like this. And then I'm going to get another 1 over R change. So something that looks along the lines of this then. All right, and then in terms of thinking about the electric potential, we'll note that this is a 1 over R, this is a 1 over R, and this is just an R dependence right here. So then how do I calculate potential? Well, I do again have to take the integral of the electric field, just as we did in the previous page. So what I am going to expect to see is I am going to expect to see two natural log functions first. One that goes something like this. Natural logs rise and level off very, very slowly. So they are unfortunately very difficult to draw. I'm sure you guys have probably realized by now that I am not the best artist, especially when it comes to sketching graphs that are such complicated things. And then finally, what I would expect to see is, because the negative integral of just something that depends on R is negative R squared, I should expect to see something that goes like negative R squared in region number 1 then. So that would be negative R squared, natural log of R, natural log of R. And this would give me a rough idea as to what the electric potential would actually look like then. And that is it for question number 1. Moving on to question number 2, we are given a circuits problem where we have a non-ideal capacitor, which is kind of interesting. Honestly, the first time I've seen a question with that, and a variable resistor. We're asked to draw a diagram that can charge the capacitor and also be used to study the current through the capacitor as it discharges through the resistor. So this is a pretty simple circuit then that we have to draw. We've got the battery. We can use more than one switch, so I am going to go ahead and do that, very similar to what I had in set number 1. And then I'm going to go ahead and have both the resistor and the capacitor in the same branch, as I did in set number 1 as well. Now this is going to be a little bit more difficult to draw, and I do actually have to put the ammeter in here. So something along the lines of that. All right, there we go. So that looks pretty good in terms of our circuit. We've got all of the necessary components. This can be used to charge the capacitor by closing the top switch and discharge by opening the top switch and closing the switch in the middle then. All right, so show that the current is given by this equation right here. Well, much like in set number 1, we do actually have to use Kirchhoff's loop rule. V sub C is actually going to be a little bit different this time, though. The voltage inside the capacitor is no longer just Q over C, but it's Q over C plus dq dt times little r of C, the resistance inside the capacitor then, because it is non-ideal. Noting that I is equal to dq dt then, V of R is going to be I times R, or dq dt, the exact same current as through the capacitor times big R then. So therefore, we get Q over C plus dq dt little r sub C plus big R is equal to 0. So solving and separating that, we find that dq over Q is equal to dt negative over RC plus R times C. Integration gives us natural log of Q is negative T over RC plus R times C, plus an integration constant. Now, we do actually know that the initial charge should be a maximum. I'm not going to go ahead and solve for that integration constant just yet, but if I go ahead and solve for Q of T, I get A, which is our integration constant, just by terrible notation. I'm just going to keep it as A. There's a little bit of calculus background behind that, but it suits our purposes well enough. All right, little RC plus R times C then. Now, how do I get current from all of this? Well, again, do note that current is equal to dq dt. And so therefore, I of t, and I am running out of space here, so let me just go ahead and draw an arrow and take up a little bit more room up here. Yeah, hopefully you guys had a little bit more room than this on your AP exam. Though, again, I am drawing quite big. I would actually not be writing this big if I had a normal sheet of paper. So you guys were hopefully fine with that overall. All right, I of t is going to be equal to I naught, which is the initial current through the capacitor. That would be what that capital A ends up being, e to the negative t over RC plus R times C, where I naught is equal to A over RC plus R times C, negative, from the derivative. All right, there we go. And that would get us correct units. A would have units of charge. Charge over capacitance is equal to voltage, and then voltage over resistance is equal to current. So I naught does have the correct units then. All right, let's go ahead and move on to the next page. This page has a graph and some other stuff, mainly just finishing off question number 2 here. And so essentially what we need to do is we are given a graph for time constant as a function of resistance, which is kind of an interesting little plot here. As usual with a graph, we do have to go ahead and draw a best fit line. So let's go ahead and see what that might look like. Probably something along the lines of this looks good. Yeah, this looks pretty good overall. Now, in terms of using the slope to calculate, the best fit line to calculate value for the internal resistance, it's important to note what the time constant actually is. Time constant is resistance times capacitance. And so the graph that we have, if I go ahead and distribute C, I would get R times C, or C times R, plus C RC. Now, if I take a look at that, that would be like Y is equal to MX plus B. So it actually turns out that the y-intercept is going to be equal to capacitance times R sub C, which is what we're looking for, is R sub C. Now, I'm not actually given the capacitance, so I can find the capacitance using the slope. Now the slope is going to be equal to c, exactly, based on my y is equal to mx plus b analogy. Well, in terms of the points that I used for my slope, I did use the points 0, 0.05, and I did do this on a sheet of paper already, because it's, again, far easier for me to do that by drawing an accurate best fit line using a ruler. I have a little bit more control over it. And then the second point is 2.25 for the resistance and 0.55 for the time constant. So that ends up getting me a value of 0.22 farads then. So plugging that in, I find that the y-intercept, which is 0.05, is going to equal 0.22 farads times RC. So therefore, RC is going to be 2.3 ohms. All right, moving on to the next page then, we have 2 parts left. The ammeter is found to be non-ideal. Is the actual value for the internal resistance less than, greater than, or equal to the experimental internal resistance calculated in part C? And the answer to this would actually be less than. Why is that? It's because the ammeter being ideal implies some low non-zero resistance that we did not account for. Now, in terms of what this would actually do, this would contribute to the y-intercept. Keep in mind, we have to actually justify our answer using features of the graph. So this contributes to the value of the y-intercept, making it overestimate R sub c. So again, more of a kind of graphical justification, which is a little bit kind of strange, but in terms of kind of elaborating on the physics, ammeter is in series, and so therefore the time constant would have RC plus R sub A, or resistance of the ammeter. And so that would just increase the y-intercept a little bit more then. All right, for the very last part, would the slope be more steep, less steep, or remain unchanged if I change the values of resistance that I have? And my answer is actually going to be remain unchanged. And the reason why is because tau is directly proportional to R. So then the same changes in R, or some change in R, would directly change tau by the same factor. Therefore, I would have the same slope. All right, and that does it for question number 2 with our circuits question for set number 2. Now moving on to the very final question. All right, in this case, we have a solenoid, one of the best, most important concepts of magnetism. And so what we have here is an induced current. We have current, not induced current, sorry. We have current going through the solenoid. It's increasing linearly with time as time goes on. Given a bunch of information, there is a lot of reading for all of these questions. But essentially, you can go ahead and pause the video if you want to read it a little bit more. I don't want to read the entire question to you. That takes too much time. But at time is equal to 2 seconds, we need to figure out the direction of the induced current. And the direction of the induced current is actually going to be counterclockwise. It should be going opposite of the direction that the current is actually going. Why is that? Because the field inside the solenoid points to the right, and this is from the side view. And then we are increasing the current. So what's that going to do? Well, that is going to get a larger field to the right. Therefore, the change in magnetic flux is going to be greater than 0. So how do I calculate that? By having an induced current point counterclockwise, it causes an induced field to the left. All right, so for part B then, we have to calculate the current in the loop of wire at time t is equal to 2 seconds. You might be tempted to just plug in t is equal to 2 for the equation beta times t. Don't do that. That is the current through the solenoid, not through the loop of wire. However, what we can do is we can figure out the current in the loop of wire, because that's just going to be equal to the induced voltage divided by the resistance of the loop of wire. And we do know that the induced voltage is the number of turns in the loop, negative, because of Lenz's law, change in flux with respect to time. Now, in order to find that, we need to note that the magnetic field through the solenoid, which is given to us on our equation sheet, is mu naught I times N, which is mu naught times big N times beta times T, all over the length of the solenoid. So therefore, phi of B, which is integral B dot dA, is going to be equal to B times A, which is going to be mu naught N beta T over L times the area of the loop of wire, which is just pi little r squared for the radius. So little r for the radius, big R for the resistance. It's pretty common notation. So I'm not going to need to specify which one is which. So it's important to note then that the induced current will be negative, induced voltage, excuse me, will be negative d dt. There's only one turn in the loop, and then of all of this stuff here. Now, what does that actually evaluate to? And unfortunately, I'm just going to go ahead and bleed over into the next section right here. So that implies that we get negative mu naught N beta over L times pi r squared. So that gives us our induced voltage, and therefore the induced current is going to be negative mu naught N beta over L times resistance pi r squared. If you go ahead and plug in all of the values that you are given, you are going to end up with a value of 0.13 milliamps. And so that is going to be the induced current in the loop of wire at time t is equal to 2 seconds. All right, so for part C, calculate the total energy dissipated by the loop of wire. When we have current, we can do that pretty easily. We know that the power dissipated will be I squared R. Well, in the loop of wire, that's just going to be induced current. So let me go ahead and write that. I induced squared times R. So the expression that we are going to get, we do have our expression for induced current down there already. So that is going to be mu naught N beta pi little r squared over L all squared times 1 over R. Well, energy dissipated is integral of power with respect to time. So that's going to be from 0 to 2. And the interesting thing to note is that power is actually independent of time. So it's actually P times delta T then. So that's going to give us 2 over R mu naught N beta pi r squared over L all squared. Again, go ahead and plug in all of the numbers. You will end up with an answer of 104 nanojoules. 104 nanojoules is what you're going to get. All right, so for part D, a group attempts to experimentally verify the calculation, and they find that it is measured to be less than the current that we calculated. Which of the following could explain the discrepancy? You can go through a similar process of elimination if you want to. The answer is actually choice B. As to why it is choice B, it's because if the plane of the loop is not perpendicular to the axis of the solenoid, then the flux actually goes down, like cosine of theta. So instead of theta being equal to 0, so you go from theta equals 0, because B and DA would be parallel if the loop is perpendicular, to theta greater than 0, but less than 90, obviously. And so therefore, noting that we do end up actually having this entire expression right here, then noting that we are going to see that because the induced current is proportional to the change in flux over change in time, that is going to decrease proportionally. All right, and so that is it for that page. We just have one more part left, and this last part is actually pretty simple. It's a little bit anticlimactic given that it's on its own separate page right here, but let's go ahead and take a look at it. So for this last part, we're told about power supply being turned off. It's a lot of reading again. All it boils down to is you have a second loop that is twice the radius of the first one, and everything else is the exact same. How does the induced current in the new wire compare to the induced current in the first wire? And the answer to this is it's going to be, the ratio is going to be greater than 2. In fact, the ratio is going to be 4. Why is that? On the last page, we determined that the induced current is proportional to radius squared. Therefore, doubling the radius is going to increase the induced current by a factor of 4. So induced current increases by a factor of 4 then. All right, and that is it for set number 2 of the E&M 2022 free response questions. And that is actually the last of the 2022 AP Physics C free response questions. So I hope that you found all of this helpful. Hopefully all of these different questions and my solutions give you a far better understanding of how to solve the questions as well. Anyway, thank you so much for watching all of these videos. I hope that you learned something from all of them, and I will see you on the next video. Take care, everyone.